In this lecture, we will deal with a single topic: how to find the distribution, that is, the PMF or PDF, of a random variable that is defined as a function of one or more other random variables with known distributions. Why is this useful? Quite often, we construct a model by first defining some basic random variables. These random variables usually have simple distributions, and often they are independent. But we may be interested in the distribution of some more complicated random variables that are defined in terms of our basic random variables. In this lecture, we will develop systematic methods for the task at hand. After going through a warm-up, the case of discrete random variables, we will see that there is a general, very systematic, two-step procedure that relies on cumulative distribution functions. We will pay special attention to the easier case where we have a linear function of a single random variable. We will also see that when the function involved is monotonic, we can bypass CDFs and jump directly to a formula that is easy to apply. We will also see an example involving a function of two random variables. In such examples, the calculations may be more complicated, but the basic approach based on CDFs is really the same. Let me close with a final comment. Finding the distribution of a function g of x is indeed possible, but we should only do it when we really need it. If all we care about is the expected value of g of x, we can just use the expected value rule. As a warm-up towards finding the distribution of a function of random variables, let us start by considering the discrete case. So let x be a discrete random variable, and let y be defined as a given function of x. We know the PMF of x and wish to find the PMF of y. Here is a simple example. The random variable x takes the values 2, 3, 4, and 5 with the probabilities given in the figure, and y is the function indicated here. Then, for example, the probability that y takes a value of 4, this is also the value of the PMF of y evaluated at 4, this is simply the sum of the probabilities of the possible values of x that give rise to a value of y that is equal to 4. Therefore, this expression is equal to the probability that x equals to 4 plus the probability that x is equal to 5, or in PMF notation, we can write it in this manner. And in this numerical example, it would be 0.3 plus 0.4. More generally, for any given value of little y, the probability that the random variable capital Y takes this particular value is the sum of the probabilities of the little x that result in that particular value. So the probability that a random variable capital Y, which is the same as g of x, takes on a specific value is the sum of the probabilities of all possible values of little x, where we only consider those values of little x that give rise to the specific value little y that we're interested in. Let us now look into the special case where we have a linear function of a discrete random variable. Suppose that x is described by the PMF shown in this diagram, and let us consider the random variable z, which is defined as 2 times x. We would like to plot the PMF of z. First, let us note the values that z can take. When x is equal to -1, z is going to be equal to -2. When x is equal to 1, z is going to be equal to 2, and when x is equal to 2, z is going to be equal to 4. This event that x is equal to -1 happens with probability 2 over 6, and when that event happens, z will take a value of -2, so this event happens with probability 2 over 6. With probability 1/6, x takes a value of 1, so that z takes a value of 2, and this happens with probability 1 over 6. And finally, this last event here happens with probability 3 over 6. We have thus found the PMF of z. Notice that it has the same shape as the PMF of x, except that it is stretched or scaled horizontally by a factor of 2. Let us now consider the random variable y defined as 2x plus 3, or what is the same as z plus 3. With probability 2/6, z is equal to minus 2, and in that case y is going to be equal to plus 1. And this event happens with probability 2/6. With probability 1/6, z takes a value of 2, so that y takes a value of 5. And finally, with probability 3/6, z takes a value of 4, so that y takes a value of 7. What we see here is that the PMF of y has exactly the same shape as the PMF of z, except that it is shifted to the right by 3. To summarize, in order to find the PMF of a linear function such as 2x plus 3, what we do is that we first stretch the PMF of x by a factor of 2, and then shift it horizontally by 3. We can also describe the PMF of y through a formula. For any given value of little y, the PMF is going to be equal to the probability that our random variable y takes on this specific value little y. Then we recall that y has been defined in our example to be equal to 2x plus 3, so we're looking at the probability of this event. But this is the same as the event that x takes a value equal to y minus 3 divided by 2. And in PMF notation, we can write it in this form. So, what this is saying is that the probability that y takes on a specific value is the same as the probability that x takes on some other specific value. And that value here is that value of x that would give rise to this particular value little y. Now we can generalize the calculation that we just did, and more generally, if we have a linear function of a discrete random variable x, the PMF of the random variable y is given by this formula in terms of the PMF of the random variable x. The derivation is the same. We use b instead of the specific number 3, and we have a general constant a instead of the 2 that we had in this example. And this formula describes exactly what we did graphically in our previous example. This factor of a here serves to stretch the PMF by a factor of a, and this term b here serves to shift the PMF by b. We now move to the case of continuous random variables. We will start with a special case where we want to find the PDF of a linear function of a continuous random variable. We will start by considering a simple example and study it using an intuitive argument, and afterwards we will justify our conclusions mathematically. So we start with a random variable x that has a PDF of the form shown in this figure, so that it is a piecewise constant PDF. We then consider a random variable z, which is defined to be 2 times x. The random variable x takes values between minus 1 and 1, so z takes values between minus 2 and 2. Now, values of x between minus 1 and 0 correspond to values of z between minus 2 and 0. The different values of x in this range are in some sense equally likely because we have a constant PDF, and that argues that the corresponding values of z should also be in some sense equally likely, so the PDF should be constant over this range. By a similar argument, the PDF of z should also be constant over the range from 0 to 2. And the PDF must, of course, be 0 outside this range, because these are values of z that are impossible. Let us now try to figure out the parameters of this PDF. The probability that x is positive is the area of this rectangle, and the area of this rectangle is 2/3. So the area of this rectangle should also be 2/3, and that means that the height of this rectangle should be equal to 1/3. Similarly, the probability that x is negative is the area of this rectangle, and the area of this rectangle is equal to 1/3. When x is negative, z is also negative, so the probability of negative values should be equal to 1/3. And for the area of this rectangle to be 1/3, it means that the height of this rectangle should be 1/6. So what happened here? We started with a PDF of x and essentially stretched it out by a factor of 2 while keeping the same shape. However, we also scaled it down by a corresponding amount. So 2/3 became 1/3 and 1/3 became 1/6. The reason for this scaling down is because we need the total probability, the total area under this PDF, to be equal to 1. If we now add a number, let's say 3, to the random variable z, what is going to happen? The random variable y now will take values from -2 plus 3, this is +1, all the way up to 2 plus 3, which is +5. Values in the range from 1 to 3 correspond to values of z in the range from -2 to 0. These values are all in some sense equally likely, so they should also be equally likely here. And by a similar argument, these values in the range from 3 to 5 should also be equally likely. This rectangle corresponds to this rectangle here, so the area should be the same, and therefore the height should also be the same. Therefore, the height here should be 1/6, and by the same argument, the height here should be equal to 1/3. So what happens here is that when we add 3 to a random variable, the PDF just gets shifted by 3, but otherwise retains the same shape. So the story is entirely similar to what happened in the discrete case. We start with a PDF of x. We stretch it horizontally by a factor of 2, and then we shift it horizontally by 3. The only difference is that here in the continuous case, we also need to scale the plot in the vertical dimension by a factor of 2, actually make it smaller by a factor of 2, and this needs to be done in order to keep the total area under the PDF equal to 1. Let us now go through a mathematical argument with the purpose of also finding a formula that represents what we just did in our previous example. Let y be equal to ax plus b. Here x is a random variable with a given PDF. A and b are given constants. Now, if a is equal to 0, then y is identically equal to b, so it is a constant random variable and does not have a PDF. So let us exclude this case and start by assuming that a is a positive number. We can try to work as in the discrete case and write something like the following. The probability that y takes on a specific value is the same as the probability that ax plus b takes on a specific value, which is the same as the probability that x takes on the specific value y minus b divided by a. This equality was useful in the discrete case. Is it useful here? Unfortunately not. When we're dealing with continuous random variables, the probability that a continuous random variable is exactly equal to a given number, this probability is going to be equal to 0. And the same applies to this side as well. So we have that 0 is equal to 0, and this is uninformative, and we have not made any progress. So instead of working with probabilities of individual points, which will always be zero, we will work with probabilities of intervals that generally have non-zero probability. The trick is to work with CDFs. So let us try to find the CDF of y. The CDF of the random variable y is defined as the probability that the random variable is less than or equal to a certain number. Now, in our case, y is ax plus b. We move b to the other side of the inequality and then divide both sides of the inequality by a, and we get that this is the same as the probability that x is less than or equal to y minus b divided by a, which is the same as the CDF of x evaluated at y minus b over a. So we have a formula for the CDF of y in terms of the CDF of x. How can we find the PDF? Simply by differentiating. We differentiate both sides of this equation. The derivative of a CDF is a PDF, and therefore the PDF of y is going to be equal to the derivative of this side. Here we need to use the chain rule. First we take the derivative of this function, and the derivative of the CDF is a PDF. So the PDF of x evaluated at this particular number. But then we also need to take the derivative of the argument inside with respect to y. And that derivative is equal to 1 over a. And this gives us a formula for the PDF of y in terms of the PDF of x. How about the case where a is less than 0? What is going to change? The first step up to here remains valid, but now when we divide both sides of the inequality by a, the direction of the inequality gets reversed. So we obtain instead the probability that x is larger than or equal to y minus b divided by a, and this is 1 minus the probability that x is less than y minus b over a. Now x is a continuous random variable, so the probability is not going to change if here we make the inequality to be a less than or equal sign. And what we have here is 1 minus the CDF of x evaluated at y minus b over a. We use the chain rule once more, and we obtain that the PDF of y in this case is equal to minus the PDF of x evaluated to y minus b over a times 1 over a. Now, when a is positive, a is the same as the absolute value of a. When a is negative and we have this formula, we have here a minus a, which is the same as the absolute value of a. So we can unify these two formulas by replacing the occurrences of a and that minus sign by just using the absolute value. And this gives us this formula for the PDF of y in terms of the PDF of x, and it is a formula that's valid whether a is positive or negative. What this formula represents is the following. Because of the factor of a that we have here, we take the PDF of x and scale it horizontally by a factor of a. Because of the term b that we have here, the PDF also gets shifted horizontally by b. And finally, this term here corresponds to a vertical scaling of the plot that we have, and the reason that this term is present is so that the PDF of y integrates to 1. It is interesting to also compare with the corresponding discrete formula that we derived earlier. The discrete formula has exactly the same appearance, except that the scaling factor is not present. So for the case of continuous random variables, we need to scale vertically the PDF, but in the discrete case, such a scaling is not present. Let us now consider an application of what we have done so far. Let x be a normal random variable with given mean and variance. This means that the PDF of x takes the familiar form. We consider a random variable y, which is a linear function of x, and to avoid trivialities, we assume that a is different than 0. We will just use the formula that we have already developed. So, we have that the density of y is equal to 1 over the absolute value of a, and then we have the density of x, but evaluated at x equal to this expression. So this expression will go in the place of x in this formula, and we have y minus b over a minus mu squared divided by 2 sigma squared. And now we collect these constant terms here. And then in the exponent we multiply by a squared the numerator and the denominator, which gives us this form here. We recognize that this is again a normal PDF. It's a function of y. We have a random variable y. This is the mean of the normal, and this is the variance of that normal. So the conclusion is that the random variable y is normal with mean equal to b plus a mu, and with variance a squared sigma squared. The fact that this is the mean and this is the variance of y is not surprising. This is how means and variances behave when you form linear functions. The interesting part is that the random variable y is actually normal. Intuitively, what happened here is that we started with a normal bell-shaped curve, a bell-shaped PDF for x. We scale it vertically and horizontally, and then shift it horizontally by b. As we do these operations, the PDF still remains bell-shaped, and so the final PDF is again a bell-shaped normal PDF. In this important segment, we will develop a method for finding the PDF of a general function of a continuous random variable, a function g of x, which in general could be nonlinear. The method is very general and involves two steps. The first step is to find the CDF of y, and then the second step is to take the derivative of the CDF and then find the PDF. Most of the work lies here in finding the CDF of y. And how do we do that? Well, since y is a function of the random variable x, we replace y by g of x, and now we're dealing with a probability problem that involves a random variable x with a known PDF, and we somehow calculate this probability. So let us illustrate this procedure through some examples. In our first example, we let x be a random variable which is uniform on the range from 0 to 2, and so the height of the PDF is 1/2. And we wish to find the PDF of the random variable y, which is defined as x cube. So since x goes all the way up to 2, y goes all the way up to 8. The first step is to find the CDF of y. And since y is a specific function of x, we replace that functional form and we write it this way. So we want to calculate the probability that x cubed is less than or equal to a certain number y.
Let us take cubic roots of both sides of this inequality. This is the same as the probability that x is less than or equal to y to the 1/3. Now, we only care about values of y that are between 0 and 8. So this calculation is going to be for those values of y. For other values of y, we know that the PDF is equal to 0, and there's no work that needs to be done there. Okay. Now, y is less than or equal to 8, so the cubic root of y is less than or equal to 2. So y to the 1/3 is going to be a number somewhere in this range. Let's say this number. We want the probability that x is less than or equal to that value, so that probability is equal to this area under the PDF of x. And since it is uniform, this area is easy to find. It's the height, which is 1/2, times the base, which is y to the 1/3. So we continue this calculation and we get 1/2 times y to the 1/3. So this is the formula for the CDF of y for values of little y between 0 and 8. This completes step 1. The second step is simple calculus. We just need to take the derivative of the CDF, and the derivative is 1/2 times 1/3, this exponent, y to the power of minus 2/3, or in a cleaner form, 1/6 times 1 over y to the power 2/3. So the form of this PDF is not a constant anymore. Y is not a uniform random variable. The PDF becomes larger and larger as y approaches 0, and in fact in this example it even blows up when y becomes closer and closer to 0. So this is the shape of the PDF of y. Our second example is as follows. You go to the gym, you jump on the treadmill, and you set the speed on the treadmill to some random value, which we call x, and that random value is somewhere between 5 and 10 kilometers per hour, and the way that you set it is chosen at random and uniformly over this interval. So x is uniformly distributed on the interval between 5 and 10. You want to run a total of 10 kilometers. How long is it going to take you? Let the time it takes you be denoted by y, and the time it's going to take you is the distance you want to travel, which is 10, divided by the speed with which you will be going. So the random variable y is defined in terms of x through this particular expression. We want to find the PDF of y. First, let us look at the range of the random variable y. Since x takes values between 5 and 10, y takes values between 1 and 2. Therefore, the PDF of y is going to be 0 outside that range. And let us now focus on values of y that belong to this interesting range. So 1 less than y less than or equal to 2. And now we start with our two-step program. We want to find the CDF of y, namely the probability that capital Y takes a value less than or equal to a certain little y in this range. We recall the definition of capital Y. So now we're dealing with a probability problem that involves the random variable capital X, whose distribution is given to us. Now we rewrite this event as follows. We move x to the other side. This is the probability that x is larger than or equal, after we move the little y also to the left-hand side, x being larger than or equal to 10 over little y. Now, y is between 1 and 2. 10 over y is going to be a number between 5 and 10. So 10 over y is going to be somewhere in this range. We're interested in the probability that x is larger than or equal to that number. And this probability is going to be the area of this rectangle here. And the area of that rectangle is equal to the height of the rectangle. Now the height of this rectangle is going to be 1/5. This is the choice that makes the total area under this curve be equal to 1 times the base. And the length of the base is this number 10 minus that number. It's 10 minus 10 over y. So this is the form of the CDF of y for y's in this range. To find the PDF of y, we just take the derivative. And we get 1/5 times the derivative of this term, which is minus 10 divided by y squared. But when we take the derivative of 1 over y, that gives us another minus sign. The two minus signs cancel, and we obtain 2 over y squared. And if you wish to plot this, it starts at 2, and then as y increases, the PDF actually decreases. And this is the form of the PDF of the random variable y. This is the form which is true when y lies between 1 and 2. And of course, the PDF is going to be 0 for other choices of little y. So what we have seen here is a pretty systematic approach towards finding the PDF of the random variable y. Again, the first step is to look at the CDF, write the CDF in terms of the random variable x, whose distribution is known, and then solve a probability problem that involves this particular random variable. And then in the last step, we just need to differentiate the CDF in order to obtain the PDF. We have already worked through some examples in which x was a random variable with a given PDF, and we considered the problem of finding the PDF of y for the case where y was the function x cubed or the function of the form a over x. What both of these examples have in common is that y is a monotonic function of x. In this case, y is increasing with x. In this case, y was decreasing with x. It turns out that there is a general formula that gives us the PDF of y in terms of the PDF of x in the special case where we're dealing with a monotonic function. So let us assume that g is a strictly increasing function, and what that means is that if x is a number smaller than some other number x prime, the value of g of x is going to be smaller than the value of gx prime. So when you increase the argument of the function increases. To keep things simple, we will also assume that the function g is smooth, in particular that it is differentiable. Then we have a diagram such as this one. Here is x, and y is given by a function of x. It's a smooth function, and that function keeps increasing. Now, because of the assumptions we have made on g, we have an interesting situation. Given a value of x, a corresponding value of y will be determined according to the function g, but we can also go the other way. If I tell you a value of y, then you can specify for me one and only one value of x that gives rise to this particular y. So the function g takes us from x's to y's, but you can also go back the opposite way from y's to values of x. And the mapping that takes us from y's to x's, this is the inverse of the function g, and we give a name to that inverse function and we call it h. So h of y is the value of x that produces a specific value y. Let us now move on with the program of finding the PDF of y. We will follow the usual two-step procedure, and the first step is to find the CDF of y. So we fix some little y, and we want to find the probability that the random variable y takes a value in this range. When does this happen? For y to take a value in this range, it must be the case that x takes a value in this range here. Values of x smaller than this particular number results in values of y that are less than or equal to this particular number. So we can rewrite the event of interest in terms of the random variable x and write it as follows. We need to have x less than or equal to h of little y. But this is just the CDF of x evaluated at h of y. We now carry out the second step of our program. We take derivatives of both sides and we find that the PDF of y is equal to the derivative of the right-hand side. The derivative of the CDF is a PDF. And then the chain rule tells us that we also need to take the derivative of the term inside here with respect to its argument. And this is a general formula for the PDF of a strictly increasing function of a random variable x. How about the case of a decreasing function? So let us assume that g now is a strictly decreasing function of x. So we might have a plot for g that looks something like this. What happens in this case? We can start doing a calculation of this kind. But now, how can we rewrite this event? The random variable y will take a value less than or equal to this number little y. When does this happen? When the value of g of x is less than y, and that happens for x's in this range. So this is the set of x's for which the value of g of x is less than or equal to this particular number y. So the event of interest in that case is the event that x is larger than or equal to h of y, which is 1 minus the probability that x is less than h of y. Because x is a continuous random variable, we can change this inequality to one that allows the possibility of equality. And so this is 1 minus the CDF of x evaluated at h of y. Now we take derivatives of both sides and we find the PDF of y being equal to, there's a minus sign here, then the derivative of the CDF, which is the PDF, and finally the derivative of the function h. Now in this case, g is a decreasing function of x. So when x goes down, y goes up. When x goes up, y goes down. This means that when y goes up, x goes down. So it means that the inverse function h is going to be also monotonically decreasing. Since it is decreasing, it means that the slope, the derivative of the function h, is going to be either 0 or negative. And so minus a negative value gives us the absolute value of that number. So we can rewrite this by removing this minus sign here and putting an absolute value in this place. Of course, in the case where g is an increasing function, when x goes up, y goes up. This means that when y goes up, x goes up. So h in that case would have been an increasing function. So this number here would have been a non-negative number. And so it would be the same as the absolute value. So using these absolute values, we obtain formulas that are exactly the same in both cases of increasing and decreasing functions. And so our final conclusion is that in either case, the PDF of y is given in terms of the PDF of x times the derivative of this inverse function. Let us now apply the formula that we have in our hands for the monotonic case to a particular example where y is the square of x and where x is uniform on the interval 0 to 1. So the function g in our case, the function g is the square function. Now, you could argue here that this function is not monotonic, so how can we apply our results? On the other hand, the random variable x takes values on the interval from 0 to 1, and therefore the form of the function g outside that range does not concern us. Over the range of values of interest, the function g is a monotonic function. So what is the correspondence? Y is going to be equal to x squared. That's the g of x function. And when that happens, we have the relation that x is going to be the square root of y. This tells us that the inverse function, h of y, which tells us what is the particular x associated with a given y, the inverse function takes the form square root of y. So now we can go ahead and use the formula. The density at some particular little y, where that little y belongs to the range of values of interest. X takes values between 0 and 1, so y also takes values between 0 and 1. So over that range, the density of y is the density of x, which is uniform, therefore it is equal to 1, times the derivative of the square root function. And the derivative of the square root function is 1 over 2 times the square root of y. As you can see, the amount of calculations involved here are rather simpler compared to what we would have to do if we were to go through our two-step program and work with CDFs. All that you need to do is essentially to identify the inverse function that, given a y, produces x's, and write down the corresponding derivative. The formula that we just derived for the monotonic case has a nice intuitive explanation that we will develop now. Suppose that g is a monotonic function of x and that it's monotonically increasing. Let us fix a particular x and a corresponding y so that the two of them are related as follows. Y is equal to g of little x. Or we could argue in terms of the inverse function so that x is equal to h of y. Recall that h is the inverse function that, given a value of y, tells us which one is the corresponding value of x. Now let us consider a small interval in the vicinity of this little x. Whenever x falls somewhere in this range, then y is going to fall inside another small interval. The event that x belongs here is the same as the event that y belongs there, so these two events have the same probability. And we can therefore write that the probability that y falls in this interval is the same as the probability that x falls in the corresponding little interval on the x-axis. This interval has a certain length delta 1, this interval has a certain length delta 2. Now remember our interpretation of probabilities of small intervals in terms of PDFs. So this probability here is approximately equal to the PDF of y evaluated at the point y times the length of the corresponding interval. Similarly, on the other side, the probability that x falls on that interval is the PDF of x times the length of that interval. So this gives us already a relation between the PDF of y and the PDF of x, but it involves those two numbers delta 1 and delta 2. How are these two numbers related? If x moves up by amount of delta 1, how much is y going to move up? It's going to move up by an amount which is delta 1 times the slope of the function g at that particular point. So that gives us one relation that delta 2 is approximately equal to delta 1 times the derivative of the function g at that particular x. However, it's more useful to work the other way, thinking in terms of the inverse function. The inverse function maps y to x, and it maps y plus delta 2 to x plus delta 1. When y advances by delta 2, x is going to advance by an amount which is how much y advanced times the slope or the derivative of the function that maps y's into x's. And this function is the inverse function. So this is the relation that we're going to use. And so we replace delta 1 by this expression that we have here in terms of delta 2. And now we cancel the delta 2 from both sides of this equality, and we obtain the final formula that the PDF of y evaluated at a certain point is equal to the PDF of x evaluated at the corresponding point, or we could write this as the PDF of x evaluated at the value little x that's associated to that y that's given by the inverse function, times the derivative of the function h, the inverse function. And this is just the same formula as the one that we had derived earlier using CDFs. This derivation is quite intuitive. It associates probabilities of small intervals on the x-axis to probabilities of corresponding small intervals on the y-axis. These two probabilities have to be equal, and this implies a certain relation between the two PDFs. All of our examples so far have involved functions g of x that are monotonic in x, at least over the range of x's of interest. Let us now look at an example that involves a non-monotonic function. We're going to consider the square function, which has the shape shown in this diagram. And we will assume that x has a general distribution so that it can take both positive and negative values. And so over the range of values of x, the function that we're dealing with is decreasing and then increasing, so it is not monotonic. How can we find the distribution of y? As a warm-up, let us look at the discrete case. And as an example of the calculation, let us find a formula for the probability that the random variable y takes a value of 9. This event can happen in two ways. It can happen if x is equal to 3, but it can also happen if x is equal to -3. And these are the two and only two ways that y can take a value of 9. We can generalize this calculation. The probability that the random variable y takes on a specific value, little y, this probability can be found by adding the probabilities of all the different x's that lead to this particular value. Now, for x squared to be equal to little y, we need to have x be equal either to the positive square root of y or to be equal to the negative square root of y. And this is the general formula for the PMF of the random variable y. And it involves two terms because any given value of little y can happen in two ways, either by having x equal to the negative square root of y, or by having x be equal to the positive square root of y. We have here a situation where the function that we're dealing with is not invertible. For a given value of y, we cannot find a single value of x that will lead to that y, but instead we typically have two values of x that lead to that particular y, namely the positive and the negative square root of y. So we cannot use the tools that we used before in the monotonic case where we dealt with the inverse function. What we can do instead is to proceed from first principles and calculate the CDF of the random variable y. CDF of y is the probability that the random variable is less than or equal to a certain number, and we're going to focus only on the case where that certain number is non-negative. If little y is negative, then we know that this probability is going to be 0 because the random variable y cannot take negative values. Now, this is the probability that the random variable x squared is less than or equal to y. So what we did here is to express this event in terms of the original random variable, capital X, whose PDF is presumably available. Now, this event is the same as requiring the absolute value of x to be less than or equal to the square root of y. And this event again is the same as having the random variable x be between the negative and the positive square root of y. In terms of a picture, the random variable capital Y takes a value less than or equal to this particular little y if and only if the random variable x falls inside this range. Now we want to express this probability in terms of the CDF of x. The probability that we're looking at, the probability of this interval, is equal to the probability that x is less than or equal to the square root of y. This is the probability from -infinity up to square root of y. But from this we need to subtract the probability of this interval. And that would be the CDF of the random variable x up to the point square root of y. So we now have an expression for the CDF of y in terms of the CDF of x. At this point, now we can take derivatives and use the chain rule. The PDF of y is going to be equal to the derivative of this expression. The derivative of the first term by the chain rule is the PDF of x evaluated at the square root of y times the derivative of this argument with respect to y, which is 1 over 2 square root y. And then we need the derivative of the second term. We have a minus sign, then the derivative of the CDF, which is the PDF, evaluated at minus square root of y, and then the derivative of this term with respect to y, which is minus 1 over 2 square root of y. Now we have a minus sign here and a minus sign there, so the 2 cancel out. We can get rid of this minus 1 term and change this minus into a plus, and this is the final form of the answer. So we see that the PDF of y evaluated at a particular point, which tells us something about the probability that the random variable takes values around this point, has to do with the probabilities that the random variable x takes values around here or around there. There are two contributions, and this is because there are two different ways that a value of y may occur, either x falling here or x falling there. In all of the examples that we have seen so far, we have calculated the distribution of a random variable y, which is defined as a function of another random variable x. What about the case where we define a random variable z as a function of multiple random variables? For example, as here, as a function of two random variables. How can we find the distribution of z? The general methodology is exactly the same. We somehow calculate the CDF of the random variable z and then differentiate to find its PDF. Let us illustrate this methodology with a simple example. So suppose that x and y are independent random variables and each one of them is uniform on the unit interval. So their joint distribution is going to be a uniform PDF on the unit square. We are interested in the random variable, which is defined as the ratio of y divided by x. So we will now calculate the CDF of z and then differentiate. It is useful to work in terms of a diagram. This is essentially our sample space, the unit square. The PDF of x is 1 on the unit interval. The PDF of y is 1 on the unit interval. Because of independence, the joint PDF is the product of their individual PDFs. So the joint PDF is equal to 1 throughout this unit square. So now let us write an expression for the CDF of z, which by definition is the probability that the random variable z, which in our case is y divided by x, is less than or equal than a certain number, little z. What is the probability of this event? Let us consider a few different cases. Suppose that z is negative. What is the probability that this ratio is negative? Well, since x and y are non-negative numbers, there's no way that the ratio is going to be negative. So if z, little z, is a negative number, the probability of this event is going to be equal to 0. This is the easier case. Now, suppose that z is a positive number. Let us draw a line that has a slope of little z. Y over x being less than or equal to little z is the same as saying that y is less than or equal to little z times x. This is the line on which y is equal to z times x. So below that line, y is going to be less than or equal to z times x. So the event of interest is actually this triangle here. And the probability of this event, since we're dealing with a uniform distribution on the unit square, is just the area of this triangle. Now, since this line rises at slope z, this point here, this intercept, is at z, and so the sides of the triangle are 1 and z, and so this formula here gives us the value of the CDF for the case where little z is positive. And the same formula would also be true if z also were equal to 0, in which case we get 0 probability. But is this correct for all positive z's? Well, not really. This calculation was based on this picture, and in this picture, this line intercepted this side of the unit square. And for that to happen, this slope must be less than or equal to 1. So this formula is only correct in the case where we have a slope of less than or equal to 1. And now we need to deal with the remaining case in which little z is strictly larger than 1. In this case, we get a somewhat different picture. If we draw a line with slope, again, little z, because little z is bigger than 1, it's going to intercept this side of the rectangle. Now, the event that y over x is less than or equal to little z is again the event that the pair xy lies below this line that has a slope of z. So all we need is to find the area of this region. One way of finding the area of this region is to take the area of the entire unit square, which is equal to 1, and subtract the area of this triangle. What is the area of this triangle? Well, since this line has a slope of z, in order for it to rise to a value of 1, x must be equal to 1 over little z. Therefore, this side of the triangle is 1 over z. And therefore, the area of the triangle is 1/2 times 1 over z, which is this expression here. And so we have found the value of the CDF for all possible choices of little z. We can draw the CDF. And the picture is as follows. For z negative, the CDF is equal to 0. For z between 0 and 1, the CDF rises linearly at a slope of 1/2, and so when z is equal to 1, the CDF has risen to a value of 1/2. And then, as z goes to infinity, this term disappears, and the CDF will converge to 1. So it converges to 1 monotonically, but in a non-linear fashion, so we get a picture of this type. The next step, the final step, is to differentiate the CDF and obtain the PDF. In this region, the CDF is constant, so its derivative is going to be equal to 0. In this region, the CDF is linear, so its derivative is equal to this factor of 1/2. So the CDF is equal to 1/2 for z's between 0 and 1. And finally, in this region, this is the formula for the CDF. When we take the derivative, we get the expression 1 over 2z squared, which is a function that decreases as z goes to infinity, so it has a shape like this one. So we have completed the solution to this problem. We found the CDF and we found the corresponding PDF. This methodology works more generally for more complicated functions of x and y and for more complicated distributions for x and y. Of course, when the functions or the distributions are more complicated, the calculus involved and the geometry may require a lot more work, but conceptually the methodology is exactly the same.